It is a pleasure for me to talk today about scalable and high-performance middleware for HPC and AI on the OpenPOWER platforms. And as of if you go back in the history a little bit, the high-end computing field has been evolving over multiple stages. Like in the last 3 decades, we started go back in 1975. It started with the traditional supercomputing and high-performance computing that is continuing. Then in the 2000, big data analytics came, like say the more simulation data or the data being collected from internet agencies. So how do we make sense out of it? Then, of course, in the 2010, the field of AI came, and that's where I think a lot of excitements are happening these days. How do you combine HPC with AI, which is a machine learning and deep learning? But then there is a new kind of a dimension is coming. That is, I call it like a computing continuum. If you take a look at it, the left-hand side here, traditional things we have been operating these days, like you have data, you have HPC centers, but now a lot of recent scenarios where data is not centralized. Data is being collected in a distributed fashion. Data might be coming from drones, data might be coming from sensors, so you need to operate on the edge or the near edge device or clouds or HPC center. So I call it like a computing continuum. And then the question is, in this computing continuum, how do you actually do all the 3 things together, like the HPC, big data, and AI? And this is where a lot of new kinds of challenges come. So take an example, like a very simple one, like a digital agriculture. I mean, traditionally the farmer, let's say, might be just spreading pesticides all over the farm based on his or her knowledge. But the question is, like, if you have a big farm, might be the different parts of the field have got different diseases. So if you spray only the same kind of pesticides, then it is not only costly, but is also not good environmentally friendly. So solutions are out there. Can I just fly a drone? And then the drone takes the image based on some predetermined model. It can on real time find out saying this part of the field has disease 1, this part of the field has disease 2. Then you instruct the sprayer or the tractor to actually go and spray appropriate pesticides to appropriate places. So these are the kind of the next generation applications are coming, and we need to see how to design such systems. So the broad challenge, again, if I take all these things together, so the plan is like how to design this high performance and scalable middleware for HPC systems with computing continuum, all these stages 1 to 4, while taking advantages of all the technologies. CPU, GPU, DPU, IPU, XPU, all these things are coming, and also the HPC and cloud resources. And this is where, if you broader take a look, let's start with the high-end side, and then gradually towards the end, I'll come to the continuum, how we are working on providing solutions. So if you take a look at the traditional, all the HPC systems, starting from Frontier, number 1, Fugaku, Summit, Lumi, and even on a lot of these clouds, we have all these commodity components, whether it is an OpenPOWER or Intel or AMD, any of these components are there. We have interconnects like InfiniBand, Slingshot, we have accelerators, all different GPUs, also the storage. So in these systems, when you want to run these applications workload, gradually also what is happening is earlier people had different workload, either focusing on HPC or AI or big data, but now there is an increasing usage of using all these things together. So you might have a complex workflow where you try to do like a first, let's say some big data stuff, followed by some machine learning, followed by HPC, or even come back to any of the other components. So that is your overall framework. So then the question is how we can design a convergent software stack. And especially that also need to run not only on the on-premise systems, but also on the cloud. And irrespective of which of these kind of the higher level software stacks you think of, you need both scale up and scale out. That means within the node, if I keep on adding more CPUs, GPUs, DPU, IPUs, I should get good performance. Then I should be able to put more number of nodes. So in this context, what we have been working on traditionally, as many of you know, MPI libraries, every time a new networking technology comes or new cluster comes or supercomputer, MPI is the first one, middleware to jump in. And that has scale up and scale out. So why not just leverage that? And through MPI, I'll try to show you solution. We have actually linked all the deep learning, machine learning, big data, everything runs on top of MPI. Okay. So in that case, you don't have to redesign all these stacks, and you will get performance portability for any kind of new architecture, whether it is a CPU architecture, GPU, or even interconnect. So that's what we have been working over the years. I'll try to give you a little bit overview of the MapIS project, and then high performance DL project, the deep learning, big data project. And here especially, I'll try to show, in fact, today morning we made the release, accelerating Spark with MPI. Spark is running over MapIS2 library. Okay. So now you name any interconnect, it is Slingshot or it is OPA, now Spark will run directly. You don't have to redesign that stack each and every time a new network comes. Same thing I'll try to show for data science. So these are all the OSU research. Over the last several years, we have also been providing a lot of commercial support and value-added product. I'll talk a little bit about that. And then I'll try to conclude. This is a new NSF AI Institute I'm leading. Last year, we got this funding of a $20 million. Many universities are working together. I'll just try to give you a perspective. And this is where we are targeting that continuum, computing continuum, how the software needs to be designed for the next 20 years. So let me start with the MapIS project. Many of the people in this room must be knowing this. We started this project almost 22 years back, year 2000, when InfiniBand came, if some of you remember, October 20th, 2020, almost exactly 20 years back. Prior to that, in my group, we were working on Myrinet, Quadrix, if some of you remember those older interconnects. But when InfiniBand came, nobody knew how to really utilize it. So we were the very first ones to come up with an MPI library, and we demonstrated it at Supercomputing O2, okay, 20 years back. And since then, we have been working on, I'm very proud of my team, 21 years and counting. Not only we started with InfiniBand, now we support all the interconnect, Omnipath, Ivar, Rocky, even the Amazon EFA, the Rockport network, Slingshot 10 and 11, Broadcom, Kernelist network, you name any network, we support. And we've been also going over all the different MPI standards, all the different GPUs. Recently also we have worked on DPUs. And this stack is currently being used by more than 3,200 organizations in 90 countries. And just from our website, we have been crossing like a 1.6 million downloads just from our website. So this is also available in like a Red Hat, SUSE, OpenHPC, SPAC. We don't keep track of those, but just from our website, we see this continuous downloads. And not only the downloads, they are being used very widely in many systems. If you take a look at it, all the top clusters, even all the cloud, Amazon, Oracle, and all these clouds, you will see MapIS library is running there. So this is what it shows. Like, just see the release timeline and download. We are on a steadily on an on-ramp basis. But internally, this is how the architecture. We started with that architecture, and we are continuously modifying. These are all our different networking technologies. These are all the different CPU, GPU, DPU architecture. And at the top level, we provide support for MPI, PGAS, and hybrid MPI, PGAS. But then we have gone up and linked it with actually TensorFlow, PyTorch, Spark. So that's what I'll be talking. But the main thing in my group, of course, we are like from an OSU side, these are our challenges. Every time a new network technology comes or new CPU, GPU, some mechanism comes. So the question is, how do we take advantage of those? Okay. And we focus on all this research. And once we finalize this research and we publish those papers, in 6 to 9 months, we actually take that into the production public releases. In my group, within the OSU, we almost work like a half research and half company. We have almost 200 servers continuously doing QA testing on these packages. So when we release it, people just download and directly it runs on very large scale systems with good performance. So in that context, let me show you a little bit more concrete numbers and all. So these are some of the releases. If some of you know, these are our stable release, 2.37 release. And this is where I'll try to show you some numbers. A few months back, we started a new 3.0 series. And this series actually not only has our older designs, it also has support for UCX and OA5. If some of you remember in the community, the community is being fragmented. Some people are going through UCX. Some people are going through Live Fabrics to support different networks. Now we support them. So that means we are able to support all of them. And in fact, there's a newer release just yesterday we call it MapIS Plus. If some of you know, we had like MapIS to GDR and MapIS to X. These were the releases which were there. Now we have unified them. So going forward, there will be two versions, MHPitch and MHPitch Plus. We call it Plus because it has more features. And this is where we'll be supporting all these advanced designs for DL, ML, big data, and data science kind of things. So take a look at the number. These are the OpenPOWER numbers. This is the MHPitch to 3. As you can see, just to get some kind of a sample number here, this is like intra-node CPU point-to-point. So that means within the same socket, two cores are talking with each other. And here we have like a 330 nanosecond. MPI latency, we can provide like a 330 nanosecond from core to core. And bandwidth-wise, here you will see like a unidirectional bandwidth around 32 gigabytes per second, bidirectional around 37. And we try to make these designs, which is like a very bare bottom to the network. With a very little overhead, we are able to send the data. This is internode. And then here we see like less than 1 microsecond. We can actually send data from node to node, CPU to CPU. And also this is like a InfiniBand. This is the last sense system in Lawrence Livermore with Power 9 CPU. So here we are able to get like a 13.8 gigabytes per second, and bidirectional is 27. So those are the CPU numbers. Now GPU also has been there for many years. I don't know how many of you have heard of this term, GPU aware or CUDA aware MPI. Some of you. So in fact, this is the concept we introduced almost 11 years back from my group. At ISC 11, we had the first paper. So the idea is that if you have systems like, let's say I have a GPU here and this is like a network adapter. If you have done any CUDA programming, most of the time what you do is of course, you have to launch a kernel to do the computation. But after that, if I want to send the data, people do a CUDA mem copy to the host, then do an MPI send, this says MPI receive, and then you do another CUDA copy. So every data has to go through these 3 hops, and it's very expensive. So what we introduce saying that just like, let's say you try to do MPI from host memory to the host memory, can we define some primitives like MPI send, but now you can say the device buffer. So you say, okay, from this device buffer, I send the data to this device buffer. So that's why it's called CUDA aware or GPU aware. And we introduced this concept. That time we worked together with Mellanox and InfiniBand. Mellanox, which was supporting InfiniBand and NVIDIA, with GPU Direct, GPU Direct RDMA, DMA copy, all those things, GDR copy, all those things we did. And if you see this animation, once you do that, everything else the MPI library takes care. As an end user, you never have to do for the communication, you don't have to worry. It automatically detects where the topology are, how the GPUs are connected. And with that, at that time, we showed GPU to GPU, 1.85 microsecond. Okay, from a GPU on one node to the GPU of another node, you can actually do the transfer on x86 platform. And that leads to very high performance and high productivity. So now if you take the same design, this is the open system, this is intra-node, that means 2 GPUs are connected on the same node. Look at the thing, 650 nanosecond, I can send data from GPU to GPU within the same node. And I get like a very high bandwidth, like a 60 gigabytes per second. Bidirectional is like 115 gigabytes per second. Again, this is on the Lawrence Livermore Lassen system. On the internode side, we delivered this very similar performance, like a 1.88. So earlier you saw CPU to CPU is like a 0.98. In another 900 nanoseconds, we were able to send data from GPU to GPU across the network. Okay, so this concept is very powerful, and it has been over last 11 years has been very widely used by all MPI libraries, all middleware. They have been trying to exploit the performance with this. And now the same thing can be extended to collectives. As you know, in the HPC, besides point-to-point, you have a lot of focus on broadcast, all reduce, all-to-all. We have been very actively working on these. And these are the numbers again on the Lassen systems. Very good performance here. You can see Bcast. You can take like 64 GPUs. I can do GPU to GPU broadcast in 3.8 microsecond. Similar kind of things we see for other collectives. Now, recently, for the last few years, now we are moving into another dimension of the GPUs, which is called on-the-fly compression. Okay, so think of like a GPU has so many cores, people have exploited it for computation. Now the question is, can you utilize it for communication? That means after I finish the kernel computation, before I start the communication, if the data is very large, let's say 2 gigabytes, 4 gigabytes, the cores are sitting idle, the GPU cores are sitting idle. Can I use the GPU cores to do on-the-fly compression and then send the data, and the other end I do the decompression? Of course, there will be overhead in the compression and decompression, but if I can reduce the message size significantly, then I'll overcome that overhead and I'll improve on latency and bandwidth. So we introduced this concept. This was a best paper finalist in IPDPS 2021. But if you see, this is actually application level benefits. Here we are running on 512 nodes on this Lassen with OpenPOWER and V100 GPUs. This is a seismic simulation. And here you will see, this is the left-hand side is teraflops per second. Higher it is better. Right-hand side is lower is better, the reduce in the latency. We can improve the application level performance by 35%, 26% kind of things, okay? And these are all available in our public releases. So just to see the impact, I mean, this year I'm trying to show some numbers on the Oak Ridge Summit, you know, the OpenPOWER system, which is used to be #1. And these are the testaments from like the University of Tennessee people across different MPI, Spectrum MPI, MAPH, OpenMPI, UCX. MAPH is actually delivering the best performance on the Summit systems. Similarly, like this is the Idaho National Lab. Some of you know they do a lot of nuclear energy research. In addition to MPI, like they use a lot of upper level software stack like Moves, PETC, libmc kind of things. And this was a presentation. Their lead person presented at we do an annual MAPH user group conference. So in August, look at the things. The last year, this is their statistics. The users are using all the different MPI libraries, but starting from 2002, so this is the MAPH 2. So everybody has moved to MAPH 2, okay? Because this is where they get the best performance and scalability. So that shows the kind of the testament. And very interestingly, I'm very, again, proud of my team. All of you must have heard of, like last month, this NASA's DART mission, okay? The NASA sent this aircraft which hit into the asteroid, like a planetary defense. MAPH 2 was used here. So this has been through Lawrence Livermore from 2016. Last 6 years, all the simulations related to NASA DART mission is running with MAPH 2, okay? And this is how exactly they were able to predict like how it will go, how it will hit, what impact kind of things will be there. So this is what just like a few examples. I'm just trying to show how MAPH 2 is helping all the different users purely from HPC. But let me go into the little bit of the deep learning side. So here what we have done, again, the deep learning, as most of you know, like they are using TensorFlow, PyTorch, or MXNet. How many of you have heard of this? Or about torch distributed and deep speed? Some of you. So these are the kind of the middlewares where on top of these, all the other frameworks are sitting. So what we have done, we have actually linked those to MPI. Okay. This is the MAPH 2 or MAPH 2X for CPU-based training, MAPH 2 GDR for GPU-based training. So now since the MPI, our MAPH 2 library provides good scale up and scale out, now you can actually, for all your applications, you will get the good performance in a transparent manner. So this is the project we call high performance deep learning. You can go to this site and download our packages, and I'll try to show you some sample numbers here. So look at this on the Oak Ridge Summit. Okay, this is a little bit older numbers, but we are able to scale up to like, see the 1536 GPUs. This is ResNet 50 training with the ImageNet 1K with 1.2 million images. We are able to train it in just 4.5 minutes. Okay, because we are able to provide that kind of a scale up and scale out. This is some recent work. This is like a Lawrence Livermore OpenPOWER system up to 1,000 GPUs. This is the model parallelism. The previous one is data parallelism. Now, recently, many of you know the model sizes are becoming so large, data sizes are becoming so large, you cannot fit them into GPU. So you cannot actually run data parallelism. So we have been investing a lot on model parallelism and hybrid data parallelism and model parallelism. So this is just trying to show the model parallelism. Trying to give you like a very good, on 1,000 nodes, we are able to give you like a scaling efficiency of 97%. Look at some of the like the transformers model, which are very widely used for like the language interpretation. So there we have been able to, again, use our model parallelism going into advanced thing called a subgraph parallelism. And here, if you see the performance, compared to data parallelism, we are able to push the performance by a factor of 3. Okay, so these are some of the samples number, and many of the slides that you can see below is the actual paper. So those papers goes into more details on the design. This is a very classic use case. We have been working with a computational pathologist. You know, the healthcare cost in US has been steadily rising. Just take the simple example of pathology. Every day, so many pathology images come to an hospital. Now the pathologist, let's spend 15 minutes. Can we actually develop deep learning model on those pathology images? So as soon as you go there, your sample is taken. Within few minutes, your deep learning model will say you might have disease X, Y, and G. And then the pathologist will come and then might be spend only 3 minutes and have a proper diagnosis. So when we started working with these people, they were like taking almost 30 hours to train. But then we worked on, this is actually on the OpenPOWER systems. We are able to reduce it to almost like a 24 minutes. So we are able to give you like up to 128 GPUs. There was a 15x reduction in the training time, and also almost 22x improvement in the speed up. So those are the deep learning, but there are also a lot of applications on machine learning, like the standard supervised learning, unsupervised learning, reinforcement learning. So here what we have done, there is a package or an environment called as QML. NVIDIA has been pushing on that QML. But what they do is they basically provide support for UCX library or their Nickel library. Some of you might be knowing NVIDIA Collective Communication Library. What we have done, we have linked through an MPI for Pi, and we have linked it to our MAPISTO library. Again, the objective is the same, to get a scale up and scale out. So in fact, today morning, we made this release. You can take a look, MPI for QML, and you can download from our site and look at the numbers. So these are like the k-means, nearest neighbors, truncated SVD, linear regression kind of things. There are 2 bars here. So here is the green bar is the nickel, and the blue bar is our MAPISTO. If you use the MAPISTO, we get improvement almost like a factor of 1.6, 1.4. Okay, so hardware is the same. It's just using the optimized software, and this is the convergent software stack we've been talking. So because MPI provides a very good scale up and scale out, any of the stacks you can layer on top of it, and you will be able to get good performance. Same thing we have been doing of the big data side. This is the high performance big data project. Some of you might have heard of. This is like a 2013 we tried to work on. So we have designed like RDMA for Spark, Hadoop, Kafka, HBase, Memcached. So this project has been continuing, and these solutions are already available for x86 and OpenPOWER. So here we did a lot of work on rewriting the software stack over InfiniBand, so that directly they get the good performance. But then what happens is, let's say Slingshot has come. Now we have to rewrite, or OPX has come, we have to rewrite. So then we changed our design, saying that, okay, instead of rewriting to every network, can we link it with MPI? Okay. And this is where we have now MPI for Spark. Again, today morning, we made this release. Go and take a look at it. So what we have done is, those if you're familiar with the Spark architecture, at a bottom layer, there is something called netty. And that netty, we have linked it with the MPI library. So now if you see, you can how much performance improvement you can get. These are on across different systems. These are some of the benchmarks. Compared to standard Apache Spark, you get almost like a 3.65x improvement. Even compared to our RDMA Spark, which we had done earlier, we still get 1.88 improvement. This is surprising because you see that Spark design we did like almost 7 years back. So now MPI has been continuously being optimized. So we are able to directly leverage that. So that is the beauty of this portability, performance portability through MPI. Now we can actually accelerate even the Spark. So the other thing which is coming up, how many of you heard of Dask stack? So that is for the data science. A lot of people are using that Dask. So now we have linked that to also to the MPI library. So this is a release called MPI for Dask. And here again, these are very latest number on Cambridge systems from UK. Again, currently users are running over either TCP or UCX, but now look at the MPI. The lower is better. And here we can see this, the left-hand side is the right-hand side, higher is better. We can actually give you almost factor of 2 improvement if you use the MPI library. So that is all our a design kind of things. What we have done is everything we are trying to bring through the MPI. So then as we move forward, anytime there is a newer processor, newer GPU or newer interconnect, as soon as the MPI library is available, you should be able to move that performance to any of the upper level middleware. So I just want to say this, a lot of this, what I'm talking is actually been translated into a book, MIT Press book, High Performance Big Data Computing. In fact, here at the SC floor, MIT Press will be having a very special opening during the gala opening. If you are here on the exhibition floor, please feel free to stop by on the MIT Press booth. They will actually try to do a raffle, and free copies of this book they will distribute. Okay, so you can look for it. Now, these are, of course, all the OSU side we are working on. But then over the last several years, people have been asking us commercial support. We have the software, of course, from the OSU side, anybody can download, anybody can use, anybody can ask questions. We answer those, but still people want very optimization, tuning, bug fixes. So this is where we started this commercial spin-off called Xscale Solution. Actually, it is also a member of the OpenPOWER Foundation. And through this, we have been able to now provide support to a lot of national laboratories, international HPC centers. Our largest customer is actually Lawrence Livermore National Lab. They use all of our libraries, and many of their like the top 500 systems use our stack. So through this, not only we are able to provide commercial support, but we have been providing some value-added products. So whatever solutions I provided, like I indicated from the OSU side, we can go one step further. So this is where like we have packages, Xscale HPC, Xscale AI, MIPS to DPU, Xscale AI DPU. I'll just talk about only one of them, like Xscale AI. So this is where we have taken that combined. I mentioned about TensorFlow, PyTorch, and all running on top of Horobot, running on top of MPI. But now on top of that, we have not only optimized it, we have also provided a lot of like a very integrated profiling, introspection support, checkpoint, restart support. So now if you take a look at it, this is on the OpenPOWER system. If you go through the standard Horobot, you can see, oh, I can download the Horobot and I can run it on system. You will get good performance. But this is on a 512 300 GPUs on OpenPOWER. This Xscale AI package will give you 36% improvement. Okay, the higher kind of the images per second. It also has a very detailed deep introspection, just like a car dashboard. You can actually see while the job is running, what is happening to the already use, which is the most frequent, where the time is being spent, so that you can very quickly tune it. If you don't have this kind of software stack, it takes for a developer weeks or something to optimize your workload. But now with all this deep introspection, you should be able to solve this in few hours. Similarly, we have now provided a checkpoint restart support, because these deep learning jobs, as you know, run for days and all. If suddenly a node fails, then you have to restart. Of course, PyTorch has some basic checkpoint restart support, but see the performance. Overhead is very high, whereas we are able to give very good designs. This is based on the, from Lawrence Livermore, there's a package called SCR, Scalable Checkpoint Restart. So we have actually integrated that. And similarly this is also for PyTorch over Horobot, similar kind of things we give. So these are all the kind of the traditional, like the stage 1, 2, and 3. But here, the next phase comes. This is the new AI Institute, a $20 million for 5 years we have got. It says intelligent cyber infrastructure with computational learning in the environment. So let me play a short video here. It'll give you the perspective of what we are trying to do.
Is about how many other patents will that tracking, while distributors and public divisions are circulated classified data services will have delivery to communities. Knowledge can provide written models, tackle range of needs such as biodiversity, conservation, and cultural and consumer needs. But we still allow the infrastructure for the cross data and models. Different complex functions for diverse data requirements. Even in-house service first, there is standardized the problem because the standardized microphone is ready to be that's something exists. Under unable, including supplementation will be earlier than national AI-driven computational the functions and utility much the power of the water and information. This new utility will enable the delivery of lines and uses with global search. They will be solutions for human problems of national, regional, and global influence. Will provide an operational roadmap and framework for a cycle infrastructure that enables wide and easy access to market data. Plus, the conversational interface allows stakeholders to diversity, ask questions, and receive answers informed by highly available data knowledge. For example, food distributors learn to create standards and music products might ask most of the questions will learn to be active in version 7. Not respond to them. State in your under forecasts of running commitments and currently all kinds of scenarios. Okay. So whether one is lines, acquire inventory at work with producers, processors, distributors, transferring networks, wholesalers, and retailers throughout the region. Use AI models to forecast supply chain conditions, marketing volume, and alternative services that can consistently supply or vulnerable populations and accident the product disruption. They target level different data from other locations, multiple times. Principal will even work on assembly, high-performance indicators, backends, and learning how to video legacy skills, cultural production, and we all supply infrastructure. So avoid similar disruptions. Significant work is not a smart home infrastructure elements. Artificial producers have been falling together to sometimes without work stakeholders. They will also attention to transform the environment from considering the climate issues for the climate to one their long time AI and integrated bottom in how diverse end users with knowledge and data books that are science-based, traceable, transparent, usable, and flexible, increasing AI for speed for AI for
So this is where we are looking for the next 20 years, how this field of the AI, HPC, big data, and deep learning will be all put together. So this is what, like I indicated about the computing continuum at the bottom. And then this is where the icicle sits. And at the top, we have chosen 3 verticals like digital agriculture, animal ecology, and smart food sets. But the similar designs can be actually be used for any of the newer verticals like a pathology or medicine, transportation, kind of things. And this is a very large team. I am the overall PI, but there are 14 universities involved from coast to coast. There are 46 PIs and almost 60 students. So they're like a 100-members team are working together. And of course, inside this, there are a lot of different projects, foundational systems AI, like how do I design model commons? How do we design knowledge graphs? How do we design the CI for AI, high performance training, high performance data management, AI for CI for AI? This is something new. How do I, while jobs are running, how do I take those log data? And then from there, I am trying to make sense. Okay, so if I'm trying to do scheduling, I have all my past data. And based on that, I can actually predict how the next scheduling should happen. There is a lot of explainability, visual analytics. There are a lot of privacy, accountability, data integrity issue. And the plan is to really put together this software. We'll have an Icicle-based software and then Icicle domain-specific software, like Icicle digital agriculture, Icicle animal ecology, kind of things. So we have a lot of cross-cutting projects. We also, there's a very big focus on co-design actually on our team. There are actually faculty members from food of agriculture, food distributions. So they're not computer science people. We are working together with them to come up with the solution. And of course, there is a lot of focus on BPC, diversity, inclusion, kind of things. So I'll not have time to go over all those details, but here at the SC, at the OSU booth 1435, we have 2 special presentations. And then, of course, at the OSU booth, as you know, we have like almost 3.5 days of continuous, a lot of presentation. Please scan this QR code. You should be able to stop our booth or go to this site. If you look at the MAPI site, there is a link there, and you will see all the talks we'll be presenting, not only from our team, Icicle team. We also have a lot of external team, like Azure, INL, a lot of external visitors will also be giving talks. And we'll have a free t-shirts for all of you. So please feel free to stop by there. So with this, I'll conclude here. As I started saying, of course, the exascale system, we have just seen one. Hopefully on Monday, we'll see some more announcement. So like this, you need to take a look at a holistic view of this HPC big data deep learning to really design the software stack. And I provided some overview and opportunities and some of the solutions. But then as we have the exascale, people have already started talking about the data scale systems. Okay. I mean, that will be 1,000 exascale. I don't know how soon we'll get it, but the challenges will be even harder kind of things. And we need to keep an eye on this. So with this, let me thank all our sponsors. But more importantly, these are all my heroes. What I'm just presenting here in 30 minutes is actually work of almost 100+ people who have been in my group from the past, current, and all the students and staff. So those are all my heroes. So every time I give a talk, I really want to acknowledge their contributions there. So with this, I'll conclude here. I'll be very happy to take any questions, but I'll be here until Thursday afternoon. So at the conference, we have a lot of events throughout. So I'll be happy to talk with any one of you interested.